Thank you for having me here. I think I'm hitting the right button. Mike Vildeville, responsible for worldwide sales at Apro. Just a couple of slides to introduce you to Apro. Many in Europe are not familiar with my company, and so I thought maybe a slide or two just introducing the company and then introducing our role in this project. So Apro has actually been in the business for over 20 years now in the US, starting out as an OEM contract manufacturer, building systems for other partners such as Cisco and Sun Microsystems at the time. In the early 2000s, branded our own servers under our own brand, and beginning about 6 or 7 years ago, began focusing exclusively on the HPC market and developing HPC solutions exclusively. If you look at the top 500 list that was just published this week, we have clawed our way to the number 4 vendor position on the list. We are the number 4 vendor in terms of number of systems on top 500, as well as number of flops represented on top 500. So the company continues to grow quite rapidly and offering some very compelling HPC solutions today, predominantly in the US and Japan markets, and continuing to grow into other geographies. We focus our solutions not only on capacity systems, which really was what the company started doing 5 or 6 years ago, but now developing and deploying data-intensive hybrid computing systems and capability configurations as well. And we have a line of blade products which are very popular in the US, and an entire line of blade systems based on Intel processors, Intel motherboards, Intel mic coprocessors. So getting to the collaboration, so Apro, as a model of our engagement with our customers, we often engage in collaborations, technical collaborations with customers. We have been doing Knights Ferry related collaborations with a number of partners in the US and in Asia, including Sandia, the National Institute of Computational Sciences at the University of Tennessee, Oak Ridge National Lab, and KISTI in Korea. And our strategy on Knights Ferry early development activities and early Knights Corner deployments has really been around clusters. So although many customers have received single SDK kits for Knights Ferry, what we've been doing with customers is deploying small clusters, InfiniBand clusters of those SDKs, and doing analysis of applications not just in the mic, but more importantly, and more relevant to HPC, is how clusters of mics work together, especially on InfiniBand networks. So just want to let you know, the 3 organizations, Apro, Sandia, and Intel, did come together with a very clear idea of what we wanted to accomplish in the collaboration, structured the collaboration around that, and now have executed toward that, and we're very pleased with the outcome and the progress. I'm often asked, what's the kit or what's the hardware and how did we deploy it? So the quick answer is we did a multiple phased installation. Phase 1, we installed testbed platform based on Westmere systems and a cluster of InfiniBand cluster of Knights Ferry SDK kits. We upgraded that to Sandy Bridge, and we did that, by the way, prior to Supercomputing 11, and so that Sandia was able to publish some results on that early system. We've since upgraded the system to Sandy Bridge, and then phase 3 will be to upgrade that furthermore to pre-production Knights Corner systems to continue the evaluations. Also, software and other support tools are also part of this collaboration to make sure that these systems are manageable and maintainable. How does this fit into the context of what Apro is doing in the market and in other geographies? This is a good example, this collaboration, of what Apro refers to as our hybrid computing platforms, where they're GPU or mic accelerated systems. But we also have similar activities with other customers around capability systems, capacity systems, and data-intensive architectures as well. We view these types of collaborations from a vendor's perspective as very important. We prefer not to go and develop next-generation HPC systems in a vacuum, but rather we'd like to do it in a collaborative model with real customers who are solving real problems. And we see a lot of value coming back to Apro as a result in allowing us to better design our systems, to make sure that we're achieving the right performance targets, offering the right features, providing the right flexibility, even some of the more minor issues that might affect how maintainable the system is. These are very important issues when we're designing our products, and these collaborations really provide a lot of input into our design process. And of course, performance as a function of price. So I'd like to hand it over to Jim and make sure that we have ample time to cover the meat of this collaboration. So Jim, thank you very much.
Okay, so my name is Jim Ang. I'd like to acknowledge very quickly a number of collaborators, a lot of staff in my department, and also a sister department that focuses on scalable system software development. We've been using our mic cluster for three main areas of activity. One is, which I'll spend most of the time talking about, using this as a platform for collecting data on our mini applications. We have a set of proxy apps. This is an open website. The idea here is to develop a series of applications that characterize how our real applications make demands on the hardware capabilities of new advanced architectures and emerging systems. We're also working on the development of an open framework for architectural simulation. It's called the Structural Simulation Toolkit. This is also open source and available on this website. Lastly, Sandia has a long history of developing lightweight kernel operating system software. And Kitten is the current variation that's open source, and again, it's available on that website. One of the buzzwords that everyone talks about is co-design. And I wanted to just share with you how this test bed is one of the strategic capabilities that we view as critical for co-design. I mentioned, so we have really the test beds, we have architectural simulation. I already mentioned Mantivo is our set of mini applications. Mini apps, by their nature, are supposed to be a proxy for real applications. And the real applications are typically too complex, too unwieldy to work with a company on. And then finally, there was a discussion at this morning's Exascale session where Michael Resch was pointing out, well, architectures are often proprietary. And so we can't actually deal with good definitions of a computer architecture. And I'm sure Intel would be, even though our collaboration is very good and strong, Intel would be reluctant to share a lot of the internal details of mic architecture. So what we try to do then is develop abstract machine models, which are essentially a proxy architecture. There's a symmetry with the proxy applications that this model is greatly simplified, but it's also of a scale that we can manage and deal with. So we're trying to develop, in this case, an SST simulation of our mic architecture cluster. And then all these arrows indicate really the interactions where co-design can actually occur. Been focusing on three different ones: molecular dynamics, finite element, and really ghost cell communication for one of our hydrocodes. Implementations have been developed for actually the MPI plus X, and actually I'm missing one. There's the plus OpenMP plus Silk Plus and plus P threads. I'll come back to this later. We're also looking to exercise one of the points Rajesh was making, that we can use a single code base run on both Xeons and Xeon Phi. Now, with respect to the comments on the heterogeneous clustering and homogeneous clustering, to be honest, we haven't experimented with heterogeneous clustering yet. So we've done experiments with the offload model and what we've called native, which is the equivalent of homogeneous clustering. We've developed, again, versions of our mini apps to exercise both of these types of programming models using a number of different threading models. And there's really an ongoing assessment that we're still engaged in to understand the trade-offs, but at least quantify the trade-offs between these different approaches. We are looking at at using the same code, running it on both the Mike architecture and then comparing with Westmere and Sandy Bridge. So we are looking at and taking advantage of Intel support for intrinsics, the AVX and SSE instructions. And we're seeing very good speed up in terms of how the code performs on the Mike coprocessors. Mike already showed a picture of our cluster test bed, and I'm sure like many of you here, we also have a number of developer cards. Earlier this year, we received a Knights Corner Alpha developer card. This summer, we hope to upgrade our cluster to Knights Corner as well. With respect to Knights Ferry, we have done testing at scale. We had to develop an experimental MPI implementation. It's clearly not optimized, and to be honest, we're not going to try to optimize it because it will be upgraded here very shortly. The important thing here is that we've run our Mini FE proxy app on the whole system utilizing over 10,000 threads. So at least in terms of scalability, it seems to work well. All right, real results. So this is a set of test results on Knights Ferry using 3 different problem sizes, and within the context of each problem size, we're looking at a strong scaling problem. So you can see the 4 different problem sizes, rather. In the 100 cube size, we're actually in a regime where we don't have enough computing work, so the application is kind of communication bound. You're probably not used to seeing a strong scaling curve that goes up, where we're plotting a runtime of the conjugate gradient solve time within this application. As you know, typically you'd see a curve like this one. And this is with the largest problem size, where as you go to add more computing elements, your actual solve time, runtime decreases. And the point I'm just trying to make here is with these different problem sizes and the shapes of the curves, it's consistent with what we would expect, that we're in a regime and we can change the problem size to tip the balance to either a scenario where we're communication bound or compute bound. Most of the time you'd want to see a curve like this, and we don't have a curve at 2 Knights Ferry cards because there isn't enough memory for this largest problem to fit there. There's a call for increasing memory capacity, right? This plot is actually now normalized. We're talking about speed up of Mini FE on Knights Corner versus 1 socket of Westmere. This is, again, the Mini FE application running a range of different numbers of threads and for different problem sizes. And this is actually reasonable performance to see that the largest problem size, the largest number of threads, we're seeing a speed up of almost 2.4 over a Westmere solution. And again, it's the same code, same Mini FE implementation using intrinsics. And then finally, here's a comparison of Knights Corner performance versus Knights Ferry using either 120 threads for these 2 sets of bar graphs and the full maximum amount of threads that Knights Corner can provide. So Knights Corner in double precision using all the threads is more than 3x the performance over Knights Ferry. Ideally, I could show you our results with our Mantivo proxy apps, and we're not quite there yet. But what I did want to show you was some results from just last week, where we're using LM Bench, the memory benchmark, looking at running the benchmark on the Knights Ferry, and then also running it as a driver for our architectural simulator. And in this case, the experimental results are in blue, the test results on Knights Ferry, and then in red or green are our SST simulation results of Knights Ferry. And so we have a plot of latency versus array size, memory size. And so this is actually showing when you overflow the caches, L1, L2. On the left-hand side actually shows the results of the tuning that we can do within our architectural simulator. So obviously, the comparison of these green curve, or the red curves here with blue is not good. And that has a very simplified model for the processor cores on Knight's Ferry. In green is a new set of parameters that track much better. And this is still work in progress, but this is a plot of the memory bandwidth versus array sizing. So once we have these things optimized, then we can go back and rerun with our proxy applications. So, and this is where we don't, without knowing the details, the proprietary details of the Knight's Ferry hardware, we can still use our architectural simulators to, work with our test bed and understand how to improve our applications. Finally, just one slide. I won't brief this since this isn't my work anyway. But we have ported Kitten to a Knight's Ferry card. Interestingly, Knight's Ferry doesn't have a console, so we think it's working, but we can't really tell. We're working with Intel, and our software team is going to go visit, spend some time in Hillsboro to work with a special version of Knight's Ferry that will have a backdoor. So that's work in progress. In conclusion, our early experiences with Intel Mic have been very promising. Hopefully, I'm just giving you a flavor of the results we're getting, but it's being used to help us with optimizing codes for the Mic architecture. Again, we're exploring a number of the different programming models. Finally, we're actually very excited about the ability to upgrade the system to Knight's Corner when we can then use Intel MPI. And at that point, have legitimate scaling results to share. So with that, we'll take questions if there's time.
I just have two questions. One is in the first talk, you stressed a homogeneous programming environment with MPI, but in the application still you have a hybrid, so it's similar like MPI and CUDA, in some sense.
Right.
So how will it be possible to have some support for really homogeneous MPI applications? And the second question about the cache in your language. I mean, how much memory and how much can the user program the cache on the mic cores as it is possible?
And I'd probably call on some of my software partners to deal with your first one. In terms of the cache size, I think we have clearly shared that with Knight's Ferry. You have the level 1, level 2 cache. These are coherent across all the cores. And I believe the number that we have shared is 8 megabytes. Okay, so that's sort of on die, pretty decent memory sized. And then you use, I think it's 2 gigabytes on Knight's Ferry. The memory capacity on Knight's Corner hasn't been formally disclosed. So that's the second part. I think the first part, let me just make sure I was clear when I pitched it, and then we'll see if your question still remains. I think, and I think Jim, you touched on it. When we talk about homogeneous model, I think the point is, just like you were using MPI ranks on Xeon, right? So the cluster was MPI processors running on the Xeon processor cores. Now, given the Mic coprocessor has that capability of running as a node, you can run the MPI processors just on the Knight's Corner cores and be able to have it run native. Right? If you're on a system, run that application native on Knight's Corner. If you're running it on a cluster, again, the MPI ranks run across Knight's Corner. Heterogeneous, I think, that's where it gets challenging. The programming piece is easy. Having the MPI ranks run on Xeon and then on Mic or KNC is pretty straightforward. But I think the data transfers across Xeon and KNC, I think that's where the real challenges will come up, right? And I think that's something we'll have to work together. But when you have workloads that have a substantial serial component and a parallel component, right? That's where I think the challenge will be, along with the PCI data transfers. But I think that's where the heterogeneous cluster model, we think, will become appealing. So did that address your question?
Somehow, yes. But I think we just have to see more applications from the system.
Right. right. I think that's the sort of the emerging frontier.
Right. I would just add that in our experimentation, we've been in the homogeneous model, we've been changing the number of MPI ranks within a Knights Ferry card, and then balancing with threads, right? Either Silk or OpenMP.
Looks like we have a couple more minutes, so any other questions, inputs on the European Soccer Championship? Just kidding.
Yes.
My name is Franz Joseph Frank from ITWM. Maybe just information for the people in the room. We are showing at the show floor at the Intel booth two Sandy Bridge with Knights Corner with a new programming model, GPI, which is flat programming model, and you can have direct RDMA communications between the Knights Corner directly and between the Knights Corner and the Intel Sandy Bridge. So you're invited to see that. So I think it's showing great performance.
Okay, thank you, Frank.
Excellent.
We talked over dinner last night. I'm certainly interested.
So for now for ITWM, good demo at the Intel booth on Sandy Bridge and Knights Corner. Please go check it out.
Okay.
Very good.
All right. Well, thank you, everyone.
Thank you.
Thank you.